So we proved in the last class, we proved the following. Oh no. Okay. We proved the following. We proved if rho is a Gaussian state, I mean, we proved the following form for all Gaussian states. I mean, any Gaussian states will look like that. You are not there, but I hope you saw the video. Did you see the video? I did not see the video, but I saw the video. Okay. Rho is a Gaussian. So we proved if rho is a Gaussian. So there are some 4 or 5 views. So hopefully, if you are not watching, then somebody else from outside is watching that. Good. So rho is a Gaussian on L2 of Rn. Okay. Then rho equal to W of alpha for alpha in Cn. Okay. Maybe we'll write it like this. Add W of alpha, add W of gamma L, which you can put it together also, or W of alpha. Add is a where add X or U add for any unitary. We usually use it for unitary of any X equal to Ux U star or U inverse for unitary. Okay. So it is this function. B of H, any B of H. Okay. So add gamma L. Then it looks like rho of some D1 up to D1 or S1. Let's use S1. S1 up to Sn. Where rho S1 up to Sn, or that you can write it as a tuple, okay, equal to rho S1 tensor rho S2 tensor up to rho Sn. Okay. This add I will remove since you know it. And rho S equal to rho S equal to 1 minus, this is to normalizing constant because we want trace equal to 1 times E of S A dagger A. Okay, so I'll write everything. So A dagger A is a number operator acting on. So if gamma of C will look like, see, this L2 Rn is tensor product of L2R tensor L2 of R tensor. I mean, Rn is a direct sum of R and direct sum. L2 of Rn is same as gamma of Cn, which is same as gamma of Cn is C direction C. Direct sum is taken. Direct sum will become tensor product when you go to the compact, when you exponentiate. I mean, exponentiate when you go to the Fock space, symmetric Fock space. So L2 of Rn will be L2R tensor L2 of tensor n times. Okay, and in that picture, so this is this rho S1 up to Sn will look like rho S1 up to rho Sn tensor, and each rho S acts like this. This is on the kth Hilbert. I mean, this is the, see, where gamma of C, gamma of C will actually basically look like C direction C, because C, how many times you take the tensor, it's going to be C again. So it is C only. Okay. The kth thing we want to talk about, we call it as K times C. So, but we want to fix a vector. Okay. This is one, I mean, I want to put a 1 bar so that it's a vector. Okay. You take the vacuum vector, okay, which is E phi, or I mean, which is just phi or something, C times phi, or the zero vector. Zero vector is not zero vector, it is a vacuum vector. So, and then 1 bar, C times 1 bar, where 1 bar is just the some, you take some element, okay, just to note the vector, because we want to K bar times C. It's like this. Okay. Then A dagger acting on K bar is just K times K bar. This K bar is integer. Okay. Number K in that. And K bar is a vector. Kth, I mean, you fix a vector in the kth one, unit vector. Okay. It is this. It's just a number operator which eigenvector on the kth particle space. Okay. And its eigenvalue is K. It is this vector. So everything will look like this. And the alpha, and further this alpha is in Cn, and this L is a symplectic operator. L is some symplectic operator. Okay. Or you put L tilde if you want, because you want it to be complexification or whatever. Okay. L tilde or L. L is, I mean, L can be treated as a real operator on RPN or complex operator. I mean, it's again real linear only, real linear operator and a complex Hilbert space, whatever. So this is how every Gaussian state will look like. We have proved it. So we want to use this to compute something called symmetries of Gaussian state. Okay, we want to use this form to compute what is called symmetries of Gaussian state. See, we are usually interested in what are called channels. Channel is a completely positive map. I will, if we have time, we will discuss it. But in the other quantum information course, the completely positive map is defined. I'm not going to define it here now, unless it's needed. Okay, unless we have time to do all those things. Okay, so at least we'll discuss some examples. Okay, so the thing is, we want to classify all Gaussian channels. What is a Gaussian channel? A completely positive map, which when applied to a Gaussian state, give rise to a Gaussian state again. Okay, that is what a Gaussian channel is. So that question is still open. It's open. I mean, finite dimensional case, it's being solved, but in this infinite dimension, I mean, for this kind of what is continuous variable quantum information theory in this Fock space, it is still open. Okay. Continuous variable is like infinite. Yeah, this is what we are doing is continuous. Okay. See, the electron has many properties. Which property you are concentrating depends on you. This is Hilbert space. All these things are just mathematical framework for studying something in physics. Okay. So if you want to worry about only the spin of that, if you are concentrating on spin or polarization of a light, then 2 dimension is enough. But in general, electron is determined by infinite. This is position operator, momentum operator. See, you have in general, it is determined by infinite dimensional Hilbert space, which is this Fock space. Okay. Usually for electron, you have to go to fermionic Fock space, the antisymmetric Fock space. This is for the photon. These are all what are applied to photonic quantum computation, which is continuous. So you need infinite dimension. A qubit is a state here. Pure state is 7. So a qubit there is just a vector in, I mean, unit vector in 2 dimension for a finite quantum computation. Qubit space is just C2. But here it's infinite dimension. So you have to work with this when you are doing computing. Okay, so this is the general form of a Gaussian thing. We want to determine what are called Gaussian symmetrics. So, I mean, this is so determining completely positive maps, channels which preserve Gaussian state is something, of course, it's an open question, it's difficult. But we want to discuss the symmetries, means we want to compute all the isomorphisms, all the automorphism of B of H. Okay, not even isomorphism, not even homomorphism or something. I mean, not an endomorphism. It's also isomorphism. Okay, isomorphism of this Fock space, which preserves Gaussian state. They are called Gaussian symmetries. Okay. So preserves means like fixes or sends Gaussian state. No, not fixing. Fixing means it has to commute. That's all. Yeah. Okay. So it's just you can take the commutant. That's fine. Okay. It's all everything which takes Gaussian state to another Gaussian state. Okay. So U in B of H for all of our computation, H is L2 of Rn, of course. L2 of Rn. Okay, for all our purpose. Okay. U in B of H is said to be a Gaussian symmetry. If U rho U star is a Gaussian state for all rho Gaussian. That's all. Okay. If you take any Gaussian state, if you apply, this is also, we can denote it as add u of rho. Of course, the point is, hopefully I have mentioned it sometime. All automorphisms of B of H, unital automorphism of B of H, is given by this is in this form. It's given by unitary. It's in the form of add u, which you can do it. I mean, you for a matrix, for example, n cross n matrices, the automorphism of given by add u, where u is a unitary coming from the n cross n matrix. These are what are called inner automorphisms, and all automorphism of B of H is inner. They are all inner. Inner automorphism you must have studied in group theory. This is what is called inner automorphism. Okay? It should come from some. So for a general phenomenon algebra or something, this is not true. Automorphism can be outer. Okay? The automorphism need not be given by unitary, where unitary comes from that algebra. If you have an algebra, if the automorphism is in this form, where the u or whatever, I mean, it's not if you don't have norm star, then automorphism means something else. It may be invertible operator. Okay, which is if you have a group, for example, then if you have all automorphism need not be like this, no, G X G inverse in this form. This is what is called inner automorphism. Okay? So for B of H is an algebra. It need not be in this form. It is not given by any of these u.
Okay, so maybe you're considering in a bigger space some smaller subset.
There is no need like that. All these u gives an automorphism, gives a set of automorphism, which is a subgroup of all automorphism. If it's not in this, then that is a inner automorphism is a subgroup of all automorphism, right? Automorphism is a very big group. Inner automorphism is a subgroup. If it does not belong to that subgroup, then it is called outer automorphism.
X1 to GX would be an outer. Exactly how are you defining inner automorphisms?
This is inner automorphism is given by conjugation by u.
Okay, fine.
For our purpose, okay. That's not very good. Okay? This is what is called inner automorphism. Okay. So the point is, all automorphism of B of H is inner automorphism. So by this, we are determining all automorphism with this of Gaussian state. Okay? That's what I want to remark. So the theorem or lemma or whatever, let's call theorem itself. So we want to compute all u, those all u, which fixes fixes the set of all Gaussian state, the set of all Gaussian state of some particular form. Okay, so let rho t bar equal to s bar. I'm going to use t for something else. Okay. Let rho s1 bar equal to whatever this rho s1 tensor up to rho sn, okay, on L2 of R. So we have that state. Okay. I hope you have seen that this Gaussian matrix is given by the diagonal DD of the Gaussian, what is it called? The covariance matrix. The covariance matrix of this rho S is given by DD. We did that computation last time. Okay, D000D, where D is equal to D1 up to Dn, where each Dj equal to half cot H Sj by 2. Okay, so we are not going to use it, just I am mentioning it. Okay, so let rho S.
It could also be half. Nothing.
What is half?
No, like the cot H thing only comes from the 1 minus e to the power.
Right. Yeah.
But you can also have like when it's exactly half.
Exactly half. It's not cot H. No, cot H comes from strictly. Correct.
So you can have both of them.
Correct. Sure. Yeah. No. Yeah. I was only mentioning the covariance matrix of this state.
Yeah.
So that is a different thing. Okay. that will have exactly equal to half. Everything will be half, right? That's different. That is given by vacuum vector or any other vector with the covariance matrix given by L transpose L itself. It corresponds to the extreme point. Okay. So suppose U rho S bar U star is Gaussian, is a Gaussian state. Okay, is Gaussian. Then U is equal to some scalar lambda mod lambda equal to 1, lambda in C scalar W of alpha. Of course, you can see that you can insert any scalar with the U, and that is going to get cancelled. Okay, so scalar will always appear. Gamma of L, where alpha for some alpha in Cn, okay, and L is in SP to N R, okay, and there is something more which is beta of let's write A1 dagger A up to AN dagger A, where A1 dagger A is the corresponding, I mean, this A1 dagger A is the, where beta is a function. Let me explain what it means. Beta is a function from Z0 n, which includes 0, Z0 equal to, I will write 0, 1, 2, this, okay? It's just the whole number, okay? Z0 n plus, where should I write plus also, from here to complex numbers of unit modulus to the circle. Okay. See, the spectrum of this number operator, A dagger A, is integers, whole numbers, not integers, whole numbers, 0 to infinity. Okay. And so any function on this whole number, any function will give rise to an operator, unbounded operator, possibly unbounded operator. If that function is bounded, then you will get a bounded operator. If that function has modulus 1, the range of the function has modulus, range of the function is onto the circle, then it's unitary. Okay, it's clear. So what is, let's see what I have written. Beta of A1 dagger A up to AN dagger A, acting on this vector. Let me say what it is. K1 up to Kn, which is also, I call it as K bar. Okay, K is a tuple, K1 up to Kn, is going to be that beta of that function, beta of K1 up to Kn. These K1 up to Kns are numbers, okay, times K bar, where this K bar is nothing but K1 bar tensor Kn bar. Let me explain. I mean, it must be clear, but let me explain. L2 of Rn is L2 of R tensor L2 over n times. And L2 of R is C direction. I mean, L2 of R is gamma of Cn, of course, gamma of C. Gamma of C is C direction. The kth particle space is generated, it's just the C times K vector. Okay, so if you consider the first one, that is, you call it as K1 vector, the ith one is K ith vector. So if you have a tuple K1 up to Kn, you take the K1th vector, K2th vector, Knth vector, you get a vector in gamma of Cn. Okay, and those vectors forms an orthonormal basis for the gamma of Cn. On those orthonormal basis, it acts like this. So it's clear, it's well defined everywhere. And it's of U modulus 1. So it's unitary, it extends to unitary. Okay. It's bounded and it extends to unitary. It's defined on the orthonormal basis, and it takes orthonormal basis to orthonormal basis, and it's of modulus 1. Okay. So it's a well-defined unitary operator. Okay. So we have an extra term here. Okay. If it is a Gaussian, if it takes this particular Gaussian state to another Gaussian state, then we have this form. Of course, we want only lambda W of alpha gamma L as a result, actually. Okay. But here we will have an extra term. The extra term will be removed later. Okay. I mean, we are only applying for this particular state. If we apply for some other state, we will get the answer. We want to determine all Gaussian symmetries, okay, which should take all Gaussian, any Gaussian state to any other, some other Gaussian state. Okay, here we are applying for this particular Gaussian state and doing the computation now. So proof. So the thing is the getting rid of this beta. So if you apply it on vacuum vector, just not even vacuum, the coherent vectors, you will get the answer. Okay, you take the coherent vector to some other Gaussian state, and it should have, that means it, I mean, it will take pure, you will take pure Gaussian state to pure Gaussian state only. Okay, so it will be some other vector, and we know all pure Gaussian state how it looks. Okay, so we know that. Using that, it's just a computation. I will ask you to present that. Okay? Present that proof. Not tomorrow, later. No, later. Tomorrow we have fixed something, so later. Okay? Okay. One of you. I will give some another person some other one. Yeah. Okay.
Is that part of answer?
This is part of all presentation. I mean, this part of presentation, not answer. Okay. 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 So let us. I will do this theorem. Okay, which is some theoretical part is there. So I will do that, and that is basically computational part. So you do that. Okay. If you know, if you are not, I mean, it's better to present it. Okay, in the board. You can write it as assignment, but maybe it's not nice. So you will present it. Okay. Of course, the computation is in the paper anyway. So proof. So what is given? So we have this rho s bar is given by this, and it is a Gaussian state. Okay. So we know the general form of a Gaussian state. We will write that and do the computation. And they will both have the same eigenvectors and eigenvalues. You will just use that. We know this Gaussian state, rho s bar equal to rho s1 tensor up to rho sn, okay, has eigenvalues 1 minus e power minus s, e power minus summation. Yeah, it is a summation kj sj, right? Kj sj, j equal to 1 to the s is fixed, k is given by something. Kj sj with eigenvector, with the corresponding eigenvector. I forgot to add something. Let me do that now. Eigenvector, which is just k1 bar tensor kn bar, which we denote by k bar. Okay, right? And this with multiplicity 1. For that, I need something. So we have some rho s1 up to, we need some condition here. Please add it. Not bad. So let S1 greater than S2 greater than Sn, okay, greater than 0, greater than 0. Okay, I mean, it starts from 0. D starts from half. This will start from 0, right? Okay, and they are linearly independent. They are rationals, irrationals. Okay, Si in R minus Q, they are irrational and linearly independent over Q. Okay. Real number system is an infinite dimensional vector space over Q. It's one dimensional over R. Over Q, it's infinite dimensional. Okay. So you can choose any number of these things which are linearly independent.
How do we know this is rational?
How do we know? We are fixing it. We are taking it. We are taking it. We are fixing S1 grades 2. We are fixing it. Okay. We are, see, we want to compute all Gaussian symmetries. So it takes any Gaussian state to any other Gaussian, some other Gaussian state. So here I'm applying for this particular state. We are fixing some S1 up to something. This one particular state. If it takes this to some other Gaussian state, then it is of this form. So this itself gives enough answer.
Why do we need heuristically?
Why do we need? I'm just, I remembered here. So here it we need. Okay, with multiplicity 1. See, this each of these rho s has eigenvector k1 tensor up to kn with eigenvalue that with multiplicity 1. Reason is that 1. I mean, the eigenvector eigenvalue does not repeat. The reason is, I mean, eigenvalue. See, k summation kj. I mean, each of those in the tensor product, the ith one has K1 as the something. Suppose some other Sj is summation Kj Sj, then the eigenvalue will repeat, right? If it is there linearly dependent, it will repeat. So you cannot write any other Si as linear combination of other one. If you can do it, then eigenvalue will repeat, right? So here it will not repeat. So we are using it again. The linear independency, we'll use it again some other place. But here we are using it so that there is only one eigenvalue for any eigenvector. Okay? They all have one eigenvalue, and it is that. Okay, there is the multiplicity of all eigenvectors. Eigenvalues are one. Okay, they don't repeat. It's because of that. Okay. So this is fine. So we have noted that. Now U rho S bar, U star will look like it's a Gaussian state. Okay, it's a Gaussian state, is Gaussian. That implies that is going to look like some W of alpha, right? W of alpha, gamma of L times some rho T bar, right? Sorry, add up W of alpha, add up gamma of L, right? Okay, let me write it like this. Gamma of L star, W of alpha star. I mean, you should, technically, we usually use gamma of L inverse here. So that, I mean, but it's okay. L and L inverse 1-to-1 correspondent. So doesn't matter. For some alpha, alpha in Cn, L in sp2n. Okay. And T bar is something equal to T1 up to Tn. Is some in R plus. Okay, so it looks like this. So this is the statement. So if you want, we can multiply this U by W of alpha star and gamma of L in L star. So that without loss of generality, let's assume, I mean, we don't have to write it again and again. So without loss of generality, otherwise we will take a different U. Okay, we want to compute what is the U. We want to get a form for U. Okay, we take a different U. So without loss of generality, assume U rho S bar U star is equal to rho T bar. Okay, we can do that. Okay. So now we want to see what is U. We want to show that this U looks like that beta. That's all. Okay. That beta, whatever you have to just do that. The first condition, both this rho S bar and rho T bar, they are conjugated by unitary. So they will have the same eigenvalue, same eigenvectors. Okay. Not same eigenvectors. They will have the same eigenvalue. Sorry. Eigenvector will be U times that eigenvector. Okay. It's not the same eigenvector. Okay. So we will consider the eigenvalue first. Okay. Rho S bar, rho T bar has same eigenvalues. It just means those two sets are equal, nothing else. Okay. So the eigenvalues of rho S is summation Si Kj, okay, where Sj Kj, where Kj is in this, is at 0 plus n. Okay. Kj is in Z0 plus, that's fine. I don't need Z0 plus. Okay. J equal to 1 to n. Okay. This is the eigenvalues of rho S bar. This is equal to summation. Similarly, J equal to, I'm using the same J and other thing. It doesn't matter. They are different, of course. Tj, Kj. Again, Kj is Z0 plus. Okay. These two sets are equal. Okay. In particular, you can, of course, this is true for all Kj. I mean, this spans the set is where here S1 up to Sj is fixed. Kjs are varying. So you get an infinite set. Okay. There also T1 up to Tj is fixed. I mean, we don't know what is T1 up to Tj. We just know that what S1 up to S, we start with S1 up to Sn. We got a T1 up to Tn. Okay. And we got a set. spanned by the integer span of those things. Okay, whatever it is. Okay, okay. It's not span. It's a. I mean, they are all again some real number, subset of real number. Okay. I mean, this is not the eigenvalues. The eigenvalues are e power something, but just the sets are preserved. This is not the eigenvalue. Sorry, but the statement I made is not correct. These are all not the eigenvalues of rho s bar. These are all the eigenvalues of summation a dagger, aj dagger, aj. These are the eigenvalues of this, whatever sitting on the top. E power kj sj. It is the eigenvalue of that. Since they are equal, see, I should actually you should argue something. So 0 is also an eigenvalue, right? Where the vacuum vector is an eigenvector. Right? So you apply that. That will imply 1 minus e power s is equal to, so on the other hand, okay, since 0 is an eigenvalue with vacuum vector as eigenvector, okay, and it's true for both of them. Okay, rho t bar also the 0 is the eigenvalue there, right? So that imply, so that means kj is 0. There is no, the other part is not there. So it is, this just means 1 minus e power s is equal to 1 minus e power. I mean, it is not 1 minus e power. It is the product of these things. I mean, you see here it is. I missed something. It is the product of sj here, j equal to 1 to n. It's the product of these things. We are taking the tensor product, no? So this implies the tensor product of j equal to 1 to n. This product, same as by j equal to 1 to n e power minus tj. Okay, this product is there. So after cancelling the product, we get that some e power something is e power something, and e power minus is an one-to-one function. So the top part, whatever is inside there, that should be equal. So that is how we get this set. Okay, I mean, the argument is the eigenvalues are same. Because the eigenvalues are same, applying on the vacuum vector, the 0 eigenvector, considering 0, these products are same. So the constants go away. Okay, the eigenvalues of this vector is going to be this, right? This is the eigenvalue. Okay, so the constant part, whatever in the left, that goes away. Only the other summation. So those two summations are equal. Okay, so that is what he is saying. These two are equal. Okay. So from the eigenvalue, we get that these two sets are equal. These two sets are equal. Which in particular, this is true for all combination of these integers, kj. Okay. In particular, you can take kj equal to 1, one of them kj equal to 1, and everything else is 0. Something equal. So this implies there exists whatever such that sj equal to summation tj tk sk, right? tk. I shouldn't use k. K is already there. So ti maybe. It doesn't matter. I is not imaginary part. I is not the complex number. So ti k, right? I better write it in the, if you understand it, better write it in the form of this. There exists a in M and C, okay, and B again in M and C, such that S bar equal to A T bar, correct? And T bar is equal to B S bar. Reason is, you see, those two sets are equal. So to corresponding to any element here, there is some other element here. So here an element is Sj itself is an element here, taking Kj equal to 1 and everything else is 0. And for K, I mean, for other J not equal to J, you take the Ki equal to 0. Then Sj is an element here. Okay. And Sj should be summation Tj Kj. For so there exists an element which is actually this A is an integer. Sorry. It is not C. It is in fact Z0 plus. Okay. Positive integers. Matrix with entries, positive integers. Okay. We have such that S bar is equal to A T bar and T bar equal to BS bar. Correct? We have something. So in particular, this will imply A, B, B S bar, T bar, okay, equal to S bar. Equal to S bar. Okay, that's right. But since this S1 up to Sn are linearly independent, you cannot write, I mean, this means what? Summation AB I ABJ Sj is equal to Sj, right? But this is summation ABJ, maybe I here, okay, I here, I equal to 1 here. Okay? This means any Sj can be written as linear combination of other things, which is not possible. So only when I is not equal to j, it's all 0. Right? So this just means AB is the identity. The identity matrix since S1 up to Sn are linearly independent. Over Q, we are using over Z, but over Q. Correct? You cannot write one Sj in terms of other things. Okay, now AB is identity, and they are integer valued matrix. A is inverse. I mean, B is an inverse of A. Now they are just finite matrix. Okay. So this means, I mean, what does it mean? Summation Aij, some Bj, Bkj is equal to delta Ij, right? But that's possible. Only one element in the row should be 1. Everything else is 0 because it's an integer value. I mean, positive integer value. Nothing can get cancelled or something. Okay. So it just means that Aik equal to 1 for some entry, and exactly for that entry, Bkj should be. For that K, Kj should be equal to 1. So in a row, there is only one element which is non-zero, and that element is equal to 1. That's how it should look, right? Because they are all integer value, and it's going to delta Ij. So this implies, so matrix with only one element equal to 1 in a row or in a column is what is called permutation matrix. So that this implies AB or both permutation matrix, which are in particular, they are unitary. They just permute the orthonormal basis. Standard orthonormal basis, it just permute them. Okay? Permutation matrices and A equal to B inverse. And it should be A equal to B inverse. Good. Okay. Further, if K bar in gamma of Cn, of course, I mean, which is actually we are treating gamma of Cn as gamma of C, tensor gamma of C n times. Okay, K bar. So this is an eigenvector. If K bar is an eigenvector, for rho S bar, okay, then of course UK bar, the U, we want to compute this U, of course, that's our aim, okay, is an eigenvector for rho T bar, right, with the same eigenvalue. Correct? Because U rho S bar equal to rho T bar U. Okay, so if you have a K here, you will get an eigenvalue, it will pass through that, and because of this. So UK is an eigenvalue for that. Now, what is the eigenvalue? So rho S bar acting on this vector K. I mean, this K I should have written as the bra, which will be easier. Shall I change it now? Is it okay? This is the right thing. I use this K. This is the right notation to use. Okay, it doesn't matter. Okay, maybe I'll change it. Okay, you later change it. K bar to this. Okay. So then rho S bar of K, we know what it is, which is summation J equal to 1 to N, 1 minus e power minus Sj times e power summation J equal to 1 to N. K, you can write whichever the way you want, you'll get the same answer anyway, Kj. It looks like this. Okay, times K bar. Okay, so we have rho T bar acting on UK is going to the same thing. Okay. Is UK, K has eigenvalue, that eigenvalues, and UK has this eigenvalue. That's what it means, correct? That's what we get it from this equation. Whatever I have written, rho U, rho S bar is equal to rho T bar U. From that, that's what I will get. From this equation, you get this equation. Okay. From this, you have that if K has eigenvector, this eigenvector K has the eigenvalue, that eigenvalue, then this will have the same eigenvalue. Okay. So we want to see that what is the corresponding vector, which will look like 1 minus E minus Sj. But we know that this product and that product are same. So we don't have to worry about that. Okay. E power minus Sj Kj with the same UK. Right? That's what you will get. Now we want to compute UK, but we know that UK will be some other K. It cannot be something else. It will be some K prime. Right? It cannot be something else because those are the eigenvalues. Yeah, but we have to compute the Ti. I mean, if we want to compute a different Kj prime will come.
No, you wrote as
No.
Oh, same eigenvalue.
I'm just using the fact that they have the same eigenvalue. Now I want to get what is Tj. Now I want to write it this in terms of Ti using those matrices A and B and get the different Kj bar. What is the Kj bar? That's what I have to get. Okay. Now what is this? Summation Si Ki K Sj Kj, which is equal to which we can write it as S bar, okay, or even now I write it as K bar. S bar transpose K, right? As K is a integer column vector, okay, and which is same as S is equal to what? A times T bar, right? A times T bar and B or whatever. Yeah, A times T bar. Okay, so this will look like T bar. This is transpose, okay, not the same T. Transpose T bar. Okay, A transpose times K bar. No, it's the other way. T bar transpose. This T is that small t is transpose. Okay, sorry. Transpose A transpose K bar. Okay, which you can write it as T bar transpose whatever times B acting on K, right? Because A transpose A and B are permutation matrices. They are in particular they are unitary matrices. So transpose is the inverse. Okay, since B is equal to A inverse equal to A transpose. Okay. So this implies what? This implies U of K is nothing but B of K. B is just a permutation matrix. It just permutes the K. Okay. But you may have a scalar. That scalar will be something beta of K bar. Okay. Where, because I mean, you get the same eigenvector, it need not map eigenvector to exactly another eigenvector which you have fixed. Some constant times the eigenvector is also an eigenvector. So, I mean, of course, it's unitary. So the constant has to be beta of K bar modulus 1, and this is in C. Okay, it's a constant. Okay, with modulus 1. Okay. Okay. So now this UK is nothing but it takes UK to BK up to a constant. I am saying that this is nothing but gamma of B times beta of K. This is just scalar. You can write it wherever you want. Okay. So this is one thing you should realize. This is nothing but just the second quantization of B. B is a n cross n matrix. Okay. It acts on Cn. Okay. So it permutes the element in Cn. Okay. What does second quantization does? Second quantization acts on the vacuum vector as, of course, identity. See, second quantization is defined like this. Gamma of u for unitaries, not for symplectic. Symplectic means something different. Okay, that is defined only in L2 of Rn. On gamma of Cn, it's complicated. We don't know at least the form. For symplectic thing, the gamma L is defined only to L2 of Rn. Gamma of u acting on any E of some x equal to E of ux, right? But it will in fact look like gamma of u acting on anything like this phi of x tensor x squared. I mean, if you either you can define u as this, in particular gamma of u restricted to nth particle space is just u tensor n. Gamma of u acts on exponential vector like that. Either you can define your gamma of u as, see, u tensor three times. You can define it on the nth particle space. You can define u as tensor it n times on the nth particle space. Take the direct sum. They are all unitary, so it will extend to a unitary. Okay, that's not a problem. And that unitary same as gamma of u. That is clear. That is how it will act on the exponential. That is clear. On the other hand, of course, there is no other way. That is enough to prove it. So they are both equal. Okay. Or you can take it that way, differentiate it and get it. That's also, but you don't need it. You define gamma of u. You first define a different operator, for example. Okay. Where on the zeroth particle vector, it's identity. One particle vector, it is just u. Two particle vector, u tensor u. Okay. Then u tensor n in the nth particle space. You define a unitary. That unitary acts on exponential vector as EUX, right? E of x is summation x power n divided by something. So E of ux is ux power n divided by n factorial, square root of n factorial, right? So they are same. Okay. So on the nth, so this gamma of u is nothing but u tensor n on the nth particle space. Okay. Now this UK, this k is in nth particle space. Right? K is not in nth particle. K can be in any particle space. See, this is the subtlety here. L2 of Rn, let me explain. Gamma of, see, we are working with gamma of L, not L2 of Rn. Gamma of Cn looks like gamma of C tensor, gamma of C tensor, gamma of C. Okay. Here, the nth particle space, gamma of C, the nth particle space of gamma of C, even though it's one-dimensional, it is a tensor product of n times taken it, right? Right? Okay. So if you take a nth particle space of this, I mean, n is here. So nth particle space of this, okay. Nth particle, I mean, nth particle space of gamma of Cn, okay. That's going to look like, see, in this gamma of Cn, everything is going to look like something here, something, some n tensor like that. If you take the, so nth particle space of this gamma of Cn is going to look like some nth particle space in gamma of C, nth particle space in gamma of C, something like this, tensor like this. Okay. So a vector in nth particle space is going to look like xi1. This is not with the other way. That is for the anti-symmetric one. Xi1. This is the anti-symmetric tensor. You take the tensor and symmetrize it. Permute it all along and take the summation and divide it by 1 by n factorial, and that's okay. Symmetrize it. If you remember all those things, okay, symmetrize it. So it's going to look like this. Okay, Xi n. Okay, where each xi j is in Cn, right? Okay, but in anything in Cn can be written as summation. I mean, it's just a direct sum of something in C. Direct sum of Z xi m. Okay, Zj, right? Where j equal to 1 to n. Okay. Now, say maybe a n, I put it on the top. Now, if you want to talk about this m equal to 1 to n, okay, direct sum of j equal to 1 to n, Zj, where is n coming? Yeah, n. Oh, mth particle space is already there. So this should be k. I'm sorry. K. K equal to 1 to m. K equal to 1 to m. I'm sorry. This is m.
So there value decimate 2 times.
Why are you?
Z, J.
No, the xi1 mth particle space of gamma of Cn is going to be xi1, wedge xi2, wedge xi up to xim, right? That's the mth particle space, where each xi k is in Cn. Each of them is Cn. So they are in Cn means they are direct sum of j equal to 1 to n, Zjn, where Zj is a complex number, right? That's how it will look like. Zj is a complex number.
Yeah.
Okay. Now this is going to be this so j equal to 1, maybe m here. Zj k here. Okay. Okay. Now this will look like this. So if you take the wedge, this will be the sum of some Zjk is something like that. Okay. But then if you take the, what is this Zjk? Zjk coming from C. So this will be direct sum. I mean, this will be just the sum of some nth particle space in the, I mean, it is just the tensor product of how do I say that? Which is equal to That's right. The point is, I want to say, I want to see how that gamma of A acts on that. Okay. So if you have the kth vector, if you have the kth Hilbert space vector, see, if you take gamma of C, okay, for an integer k, for a positive integer k, the kth k is a Z1 tensor up to Zk or something. Okay, it's a complex number. Okay, it's written as it's a wedge of something. Okay, but still it is C only, because it's just the product you're going to take. Okay, it is just the wedge. So if you have a bigger Hilbert space, and the gamma of Cn, if you have some vector given by this decomposition, it is going to precisely this A. I mean, when U is something else, it's different. But when it is a permutation matrix, it is just going to permute these things. Okay, so if you take the nth particle space, it will precisely, nth particle space will be some nth particle space, something of C here, C here, C here, C here. It will just permute it. It will only permute. But here it is permuting in the nth particle space. Okay. Permutation means what? If you take something here and bring it here. Permutation. This is you symmetrize U tensor n acting on xi1 wedge up to xn. Okay. I mean, the second quantization of this gamma of U, maybe gamma of U. Gamma of U will look like U xi1. Okay. Here it will, I mean, for a general matrix, it will be complicated. But if it is a permutation matrix, it is just the sigma of that thing only, right? U xi1. I mean, it will not be U xi1. See, the point is, in wedge, you don't need the order. It's the same thing. You can permute it. I mean, in the antisymmetric space, you have to be careful about the sign, plus or minus. Okay. Here you don't need to. Okay. So I just write it as U xi n up to U xi n. Okay. Okay. So it is just going to permute this. If you have a permutation matrix, it will precisely permute. If you just look at precise definition, it will exactly permute it. But how will I convince you more? Is it convincing?
I'll work with it.
Yeah, you just think about it. Okay. If it's not convincing, you ask me again. Okay. One can precisely write it, but as I said, for a general U, it may be complicated. Here it is just a permutation matrix. Okay. So it permutes these things. Okay. I mean, oh, no. This user is a permutation among this, not that. Each of this Xi1, each of this Xij is in Cn. It is only permuting there.
Okay, so
It's not permuting there. It will be right. It's only permuting there. So that is what this here it's happening. Here, so when you write here, I mean, the point is when you write uk equal to bk, k is a vector. Okay? K is in k1 up to kn. Okay. Here, if it is kth vector, that kth vector will come somewhere else here.
Okay.
I leave it as an if you either convince or you write it, I leave it as an assignment to write it rigorously. If not, I will do that. Okay, it can be written rigorously. Okay, I give it as an assignment. Okay, the assignment is, you know that what you understand the definition. U of k equal to some b of k. Bk. It is just a permutation action. K is a vector k1 up to kn, n vector with integer entries. Okay, it permutes to that. Okay, that is precisely that acts on all this. I mean, there is one problem. I'm getting confused. Yeah, correct. They have, yeah. No, k can vary up to infinity. That's what there are too many confusions. Okay. K's value will be a variable. K is just a n vector. Okay. This B permutes those vectors. Now U is defined as UK going to BK. Okay. This is what is happening. K is a vector, which is K1 tensor up to Kn. Okay. Now AK is a vector, which will permute these things. Right? Okay. Now you are defining this, permute these things. So the inside the tensors. Now this K is going to AK. Okay. That is precisely gamma of A. Okay. What is gamma? Gamma of A acts on the n particle space. You know how it acts. When you are given a unitary, you know how gamma of A acts. Here the thing is, see, the nth particle space is, you tensor it m times. Here everything in our picture, whatever we have written, see, there are two pictures we are using. The picture, one picture is gamma of Cn is direct phi, C times phi, the vacuum vector E of 0, direct sum Cn itself, then direct sum Cn tensor Cn, the symmetric tensor. Okay, Cn, maybe I'll write it as a symmetric tensor. Okay, then direct sum Cn tensor n times. Okay, the symmetric tensor m times, m equal to k equal to 1 to just m times. Cn, the symmetric tensor m times. Okay, that is how it is. Okay. Now you can act this gamma A on this when A is a unitary matrix. In particular, we are using a permutation matrix. Okay. On the other hand, we are using our gamma C, which is look like gamma of Cn, which is equal to tensor product of gamma of C n times. Okay. J equal to 1 to n. I mean, yeah, write it here. Tensor product n times. Okay, n times tensor. You can write it like this. Okay. Now, each of this looks like this. C times 1 vector, C times 2 vector, okay, like this, which is tensor n times. So you will have a k1th vector here, k1th thing, k2 thing, k2 thing, kk thing. Okay. You apply the U there, you apply the gamma F here. You can, you know how to apply this, how to identify those two things. Okay. You have to identify those two things. How do you get an nth particle space here? Nth particle space, you see, you have to how do you get an n particle space in the second picture? You can take the one particle there and everything, you get an no, that will give you a first particle space, one particle space. You have, for nth particle space, you have to take the I think K1 up to, I think K1 up to Kn should be, the summation should be M, I think, mth particle space. Okay, think about it, write it. If it's not clear to you, we will do it together. Okay. It is an exercise so that you can understand this picture. Okay. So you have to see that gamma A is same in the both the picture. So that implies that our U is nothing but gamma of K times some constant. I mean, this constant is constant on B of K. I mean, this beta of K. Again, the vector K is an eigenvector with the eigenvalue beta of K, right? Right? That beta may vary for different K. So we finally found out U acts as beta of K times gamma of B. Okay. So this beta K, I mean, this is an action on the kth vector. Okay. For each vector, there may be different thing. So there exists a function. So there exists a beta from Z n, Z0 plus n, okay, to all mod z equal to 1. Okay. And there's a circle such that U is equal to beta of A dagger A, A1 dagger A1, An dagger An, okay, which we defined already, times gamma of some A. It's some circle condition. This is what we wanted. We already have some W of alpha, gamma of L. This gamma of A will be added to that. Okay. So this is the statement of the theorem. Okay. If it's not clear, you tell me what is not clear.